Hi everyone, this is our C6370 group project. Today we will present an AES 128 encryption accelerator implant on the FPGA and integrate with an HPCC program. The key idea is that the FPGA perform encryption only, while the HPS software handle input verification and decryption checks. We will show the working and the demo for the rest of the slides. So our goal is to build an AES 128 encryption accelerator on the FPGA board and integrate it with the HPS. The key requirement on plaintext is enter from the terminal with 16 characters. The AES key must be generated at runtime with no hardcode key. And the FPGA implement encryption only while decryption stays in software. For verification, the FPGA ciphertext must match the software golden AES output, and software decryption must recover the original plaintext. And this slide shows the end-to-end data flow. First, the user enters plaintext in the terminal, and the HPS generate a random 128-bit key and run software AES encryption to produce a golden ciphertext. Then the HPS write the key and PT into the FPGA using memory map register access, trigger the FPGA encryption, and read back the FPGA ciphertext. Finally, the HPS verify correctness and print all result to the console. And here's the register map used to communicate with the FPGA AES block. We use word address from 0 to 12. 0 to 3 are key 0 to key 3. 4 to 7 are PT0 to PT3. 8 to 11 are CT0 to CT3. As read-only ciphertext register. And 12 is CTRL for the start and done. On the HPS side, we use DVM, NEN, and mmap to access this register using the base address plus offset. And on the FPGA side, our AES accelerator responsibilities are address decoding for key, PT, CT, CTRL, storing the 128-bit key and 128-bit plaintext written by the HPS, and computing AES 128 encryption. The ciphertext is exposed to read-only CT register, and we provide a simple CTRL interface so software can trigger encryption and convert completion using start and done. As a design choice, we keep the interface lightweight with no wait state to simplify integration and debugging. And the software flow. This slide summarizes the HPS program flow. We read plaintext from terminal, generate a random 128-bit AES key, and compute software AES encryption as the golden reference. Then we write key and PT into the FPGA register, trigger start, and read the FPGA ciphertext back. Finally, we decrypt the FPGA ciphertext in software to confirm we recover the original plaintext, and we print the key, plaintext, ciphertext, and pass-fail states. And for the golden reference and verification strategy, we use software AES as a trust golden model to verify correctness. Our pass conditions are the FPGA ciphertext must equal to software ciphertext for the same key and plaintext, and software decryption of the FPGA ciphertext must match the original plaintext. Let's also provide anti-hardcoding evidence. The key changes every run. Different input produce different ciphertext, and the FPGA output consistently match the software golden result. And this is the demo results. For each round, you can see the generic key, the input plaintext, and the golden ciphertext. So for the demo, we input AS for 8 times, so there will be 16 characters, and we can see the results are all matched to our golden reference. And here's the resource summary. You can see the large utilization is approximately 38%, and the total bin usage is 81%. And the block memory bits usage are 13%, and ALUT usage for logic is 14,513. To conclude, we successfully integrate an AES encryption accelerator with HPS software. We verify correctness using a software golden model and end-to-end decryption check. And here's all my presentation, and we're gonna show you the demonstration. And here's the demonstration video for the Google project. So first, we just want to show you the Verilog code. And is the report for our resource. And for the filter summary, yeah. And we want to show you the platform designer. Select the QSYS. Wait a second. And here's all our platform design. You can see there's a AS128, and here's our C code. And this is our board, and now we're gonna show you how it works. So we run the AS128 and we just type a random number, and here we demonstrate use AS for 4 times and DF for 4 times, so it's 16 characters. So we can see the results are all matched to the golden reference, and now we cannot test another characters. So we use, so here's the result too. So there's all correct. Thank you.